let's start. So also I would like to show, so you'll find these videos on YouTube, on MathWorks website. So this is one of my colleague. So he is from our US office. His name is Dhirendra. So if you search for him, you'll find a lot of information around videos and content. So he's also
concept of feed-forward controls, right? And anyways, I think these are very important topics, and let's get started. Okay, so let's take a look at our robot model. We've seen in various videos before. It's a full model of the mechanics, the electronics, and the controls. Right? And so we discussed how there's really two robots showing up here. One in blue is a precise and accurate representation of the trajectory plan. The one that's multicolored, the robot that's multicolored, that's our plant model. That's one where we're basically modeling directly the mechanics and the electronics, and we're applying control theory to essentially make it move and essentially follow the blue robot. And the mere fact that they do seem to be moving simultaneously indicates that the controls are working quite well. So let's go back to the Simulink model, and I'm going to reveal a little bit more of what's going on here. You know, basically it's in this block that we got the mechanics and the electronics of the robot. It's in this block that we have the blue robot, okay, and that blue robot is used to essentially calculate ideal torques, applying essentially a feed-forward control strategy. The other thing is that there's a third robot. The third robot is used to calculate the motor trajectories. Okay, so let's show it. Let's hit run. Okay, so we'll see our, I'll call it my plant model robot, initially is in a vertical position. Now, vertical position is not a great position for this robot, and it's singular for a number of reasons. And so what we're seeing here is the yellow robot takes on what I'd call a very useful initial pose for the robot. Okay, and it's the yellow robot that's really doing, I'll call it the difficult calculation of figuring out all these different motor, angles that really give it the trajectory that we're going to want it to take. All right, and so at the end we just kind of move it back out of its initial pose into a vertical position. All right, so let's take a look and see how we did this. So I'm going to copy this motion trajectory block, and let's just open up a new model file. And we'll just paste that in. All right. Okay, and what I'm going to do is I'm going to kind of dive into it. All right. And basically we're going to see here's our robot arm. Oops, went a little bit too far, but I've probably shown this in previous videos, and hopefully you kind of recognize the image of the full robot is expressed through SimScape multibody. All right, and it's really this connection right here, right? And I am going to dive into this one a little bit, and I want to just kind of introduce this. This is that gray plate. You may have noticed it, maybe you haven't, but the whole key to this is really programming this to move the way we want it to move. Right, and I might get a little bit more deep into how we did this, but essentially there's such a thing in SimScape multibody called a bushing joint, which allows program motion for all six prismatic, or our all three of our prismatic translational axes, X, Y, and Z, as well as all three of our rotational axes. Right, and so it's in blocks like these that we really kind of program that motion. All right. And so coming back here, and you saw that I disconnected that, so let's keep it disconnected, right? And now let's hit run. All right, and so you'll see by removing that connection between the robot and the gray plate, as we did in the Simulink model, that the robot, the yellow robot's going to just flop around. And that's simply gravity acting on it, and that's just kind of the movement that you would see. Now, the programming of the gray plate actually is quite easy. Each of those axes kind of move very independent of each other, and it's really not a super difficult thing to program its movement. Okay, so let's reintroduce that connection between the gray plate and the end effector. probably can't see it, or you might barely be able to see it, but that says end effector right there. So that's the part of the robot we're connecting to. One more thing I want to do is let's introduce a scope. And I want to measure one of these signals. All right. And I do want to point out that with regard to our motors, we're making various measurements. Among those will be motion, torque, speed, and power. In this case, we're making a choice to measure motion. So I'll show you what that is when we get the numbers calculated. So by reconnecting right here the end effector of this robot to the gray plate, now the rest of the robot needs to follow that gray plate. All right, and so each of these actuators, these motors, are going to need to take on angles that will accommodate the motion of that gray plate. And so our inverse kinematics is really simply observing what those angles will be via the simulation. All right, and so the measurement that we put on it was right here for what we call the turntable axis. Right, and if we zoom in right here, we'll see there's the turntable. Here's our measurement. All right, and what we're looking at really is that it goes from a value of 0 to 90 degrees, and then back from 90 degrees down to 0. That's the yellow curve. All right, and we're going to use this information to drive a robotic simulation through the actuators. Essentially, we're going to tell the actuators how to move, and this is how we do it. And telling it simply angle versus time really isn't quite enough. We need to tell it actually the first derivative and the second derivative as well. And so the blue is our first derivative, the orange is our second derivative on this angle motion. All right, and so anyways, you'll notice in some of my simulations that I have inputs on the robot that are labeled P, V, and A. That stands for position, velocity, and acceleration. And it's by providing these signals into those robots that we can drive the motion and we can measure the torques required and the power required of these actuators. Okay, and one last thing on here, I want to bring your attention to this part of the model. That we're going to be working with a vertically oriented robot that's not in that initial pose where it's hunched over. And so for the two axes, forearm and wrist, we have an initial kind of rotation that we simply add on to the inverse kinematics that we got from the yellow robot that will essentially bring that vertical robot down to the hunched over position too. So now I'd like to take a robot that's directly fresh from CAD, and let's hit run. Yeah, and we see, fresh from CAD, it's what I call a forward dynamics robot, meaning it's receptive to torques. Well, I'll explain what that means in a second too. And therefore, it simply falls due to gravity, right? So, anyways, here's our model. Now, one of the things we do with our export from CAD is we provide two types of configurations. One's force torque being inputs. The other one would be motion. So essentially, let's just kind of zoom in on this and kind of make sure it's clear. There's your P, V, and A. All right, so this is now receptive to motion. I'll call it motion prescription. All right. Okay, and so let's just copy this. Control C. Let's come back here. This is our full model. Let's bring it up a level right here. And let's just kind of take all those signals. Instead of sending them into a bus, let's just directly send them into this robot. And so we paste it in. And control, feed them right into it like that. And now let's hit run, see what we get. All right, and so now we see it just kind of going through the motion as described by what I call my inverse kinematics module, right? Okay, and so going back to our Simulink model, we can put some measurements in, all right, and ultimately we'll do this for each of the actuators, but okay, and so that signal, which is containing an awful lot of information, let's remove that, and now let's bring torque, speed, let's just take torque and power. Okay, and we'll send that into the scope. And hit run, and let's watch the scope. Okay, and this is, basically the torque carried by that turntable motor. It's very interesting, actually, that it carries torque even when it's not moving. Okay, and that's because the rest of the robot is moving. Okay, and anyways, this is awesome. This provides us very useful information to select the appropriate motors, as well as to define very effective controls, right? And we'll see a little bit more of the design of the controls in the next video, where we will use this inverse dynamics, a model that's capable of calculating the ideal torques required of our actuators. We'll use that to define a very effective controller. Right. What I think is really interesting about what we did with this is I think we're beginning to see the pieces come together. Right. That we chose electric motors based on the mechanics. Okay. And that we are now showing a path to defining really effective controls that's actually originating from the mechanics as well as being informed by the electronics. Okay, and that's the point all along with this whole series, is that mechatronics really requires the collaboration of all these teams. So we've posted all the files we've been using in these videos on the MathWorks MATLAB Central File Exchange. And that means that the files that we're using are available to you for free download. There are various ways you can get your hands on the software tools, and I encourage you to do so and really kind of take a look at what we're doing here and see how it might work for you. So thank you very much for watching this video. If you liked it, give us a thumbs up. It's great. We appreciate it. Again, we encourage you to contact us. We'd love to hear from you. Thank you. This is Terry. Bye.
So yeah, reason why I showed you, I mean, you get a first-hand view from him what he plans to show you through these video series. Okay, so what we are able to do right now, it used to be a difficult task, right? So for example, inverse kinematics calculating. So when you hold something, there is a particular joint angles, right? So how do you calculate that inversely? Okay. So now what he showed you is basically like having a plate, move it around so that these joints take their own position. So going from complex mathematics to simplifying it, saying okay, my point is here, and you have to go from like this to this, right? So automatically your joints will be computed, right? That is one way to do it, right? And then assign, so this mechanical part, you need to drive it with electrical motors, right? So also building your electrical model into it, the controls model into it. So bringing everything together into one model so that you can solve whether you have the right motors, how much power it will consume, will it be able to drive certain load or not, right? Like those things. So how does this work? Okay. So if I take this example here, so in apps, so under apps, so you have this app called Get Mechanics, right? This is also there in that MATLAB Central link. Okay. So when you click on this, what it will do is it will open up for user file, okay, this file. So when you say browse, it is looking for this kind of file. It's not looking for any CAD file. It is looking for WM3 file, okay. And what is WM3? Okay, WM3 file is nothing but a file that is created by this tool, SimWise 4D. Okay, so this is a tool called SimWise 4D. Okay. What this does is, okay, let me show it to you. So this is a very, very nice tool. Interesting things it does. Okay. Now here you see file open. This will give you a big list of files that you can open. Okay. So SimWise for us is like a translator. So we don't have to worry about getting these files into MATLAB. Right? We just only worry about getting one file, that is SimWise file. So SimWise will take care of all those inputs from here. Okay. So you could get solid models from here, from NX, Autodesk, Solid, CATIA, ProE, okay? Or you could also get FEA results back into here, right? Okay. So let me open one Solidworks file here, assembly. Okay. So the process will look like this. Okay, here. So this is a SolidWorks assembly file, SLDASM. Okay. So you might have created this in a CAD tool. Okay. And then you open it. So it's going to convert geometry into WM3 format. Right. So this is that 4-bar mechanism. Okay. All right. Now once you've got this here, okay, you see all the parts are there. So these are the joints here. You can also see this green button here at the bottom. You can actually run this, but it falls down. Right? Okay. So what you do is we can actually fix it. We can fix this by saying fix, and then this will, everything else will fall down, this will stay. And also you see it's falling down under -z direction, right? Because that's the gravity direction. You can actually change it. You can change the gravity from here. You can say I wanted it -y. Okay. Once you do that, it will start falling in that direction. Okay. Now interestingly, once you have the mechanism, you can actually then create a joint here, right? If you have already created a joint earlier, you could also import it. If not, you can create a joint. So these many types of joints you can create. Rigid, revolute, parallel joint, linear joint, right? You could have a rope that is modeled, separator, spring, revolute, bushing, anything, belt drive, gears, okay? So let's say I want to put this fix, and this should rotate on this, right? So how this is done is, you have to create coordinates here and here on this body. Oh, sorry, I create a lot of them. Just need two, one here and one here. Okay. So what you do is you select these coordinate frames and say you want revolute joint, okay? And you say join bodies in place and create. So you get this green colored joint. Okay. So what does it mean is, basically when you run next time, okay, so it will not fall down, but it's going to rotate around that under gravity. Okay. Similarly, what you can do is you can actually place joints here as well. So I'll make the open the model that is all joints done. So it's a WM3 model. Okay. Like this one here. And you see when I run this is how it runs. Okay. So you are able to simulate the whole mechanism. This is working under gravity. You can actually run a motor. So this is running as a motor. So this joint, okay, this joint here, this particular joint is now not a revolute joint. It's actually a motor joint. This joint, revolute motor. So here you can go and say what is the angular speed and torque you can change. Right. Right. So this motor is making it run. Okay. So if I change this angular velocity, let's say, to 1 degree per second. Okay, that's not fast. So you see here, now it is running slowly, 1 degrees per second. Okay. You can even change it to 10. Okay, I have to stop it. change this to 10. Okay. So now it is running in a controlled manner. It is not under gravity that it's running fast and slow. Right? So it's running under controlled manner. Okay. Fine. Now next thing is, this is fine. What if you would like to get the FEA on this link? Okay. So you saw, I mean, it's easy to import it, build a mechanism, solve it, right? And if you want to know whether this link is will be able to take the weight of something or not, right? So you want to study this link, let's say, this one. So what option is, you basically say include in FEA. Okay. So it's got an inbuilt Nastran FEA solver. You say include in FEA. This says include in FEA, show mesh. Okay. You can go to FEA and you can mesh it. Okay. So you can refine the mesh also. So only this body has been meshed. Okay, that's what you can see here. Okay. And when you go on the run option, you have motion only or motion with FEA. Okay. So this is what I'm going to do, motion with FEA. Okay. And I say okay, then what I do is I say run. So what it is doing is, it is also solving for the motion, where it is calculating how the mechanism will move, and it is also solving for the FEA at each step. Okay. So you see that the fringe pattern for the stress is varying at every step. Right? You can actually zoom in here. Okay, let me zoom it. Like this one here. So you can have a very detailed understanding of it. You can reverse it. You see how the stress pattern is changing. And these are the forces. Now this is all visual information. Okay. Now if you want to get numeric information, what you have to do is select a body. Okay. Let's say I have selected this body. You can select a body, you can select a joint. Let's say if I select this joint itself. Okay, I want to measure on this joint what are the forces or something. So you have to go here to insert meters. So meter is to insert something to measure. So this is your constraint torque. So when things rotate, so there is a constraint torque or constraint force. Right? So I can say, show me constraint force. Okay, measured on this pin, on this link. Okay. So there we will get here constraint force, and show me also what is the one measure stress here. Let's say on this body. Insert meter and this FEA result. Okay. So I'll say insert FEA results. Okay. And one more thing I want to do is, let's say I would like to see what will be the motion of this point in the link. Right? That's also some people study. So you can put this one coordinate marker. So I want to know how this motion trajectory of this point is. Select this point and insert meter and position. Select this point. You can also say track. So I'm also tracking this. Okay. Let me put it here in the corner. So Now I run this again. So what I'm doing is, if you see, we are able to get what is the position of this point. So here, see, there is a trace going on. This is the position of that point, red circle. So there is a dot we have placed there like a marker. So this is the XYZ plot of that. This is the FEA result from here. And this is the constraint forces here. So one simulation giving you so much. One simulation giving you how the mechanism will behave and all that. Yeah. Material also you can do. You can apply to material also, yes. You can. Yes, this is steel right now. Yeah, by default. So if you go here, select a body, you can go for material, and you can change it. Right? You can select from here different types of materials and everything. No, you can put it. So when you have to put a constraint. There is no load, but there is a motor I have put here. On this joint, I have put a motor. So it is getting some load because of that motion. Okay. So if I remove this FEA and solve for only motion, it will be very fast. So this, if you see, let me show it to you what is the trajectory of this point. So this is very useful sometimes, to trace how your motion will behave in space. Okay. So this point, how that will move in space, right? It is very important sometimes. When you are trying to create mechanisms for specific application, like screen wipers or some specific kind of mechanism for some application. So for example, you see this is rotating, but this is giving you a very unique kind of position, this point. This point, if you replace here, it will be different, right? So let me show you what you can do again. You can put it here. So you can put one point here in the middle. Sorry. Okay. And let's change its color to blue and drag and 500 points, 1500. Okay. So now what you'll see is how these 2 points on the same link will trace a two different kind of trajectory. Right? Right? So they are very different kind of trajectories. Now they are very useful to understand. If you put a point here, it will be just like this, back and forth, back and forth. Right? And you see this point, this is the red color trajectory here. So it is going under some kind of a sinusoidal and in X direction, and in Z direction it is this kind of a motion. So you get feel of this display as well as numbers, and this numbers you can directly say copy data and put into Excel. Okay, so this is your time, this is your X, Y and Z, and from here also you can just go and say insert a plot. Where is it? Okay, so that's your plot. Insert this plot. Okay, that's your another plot. So these are data points you can directly extract from simulation, right? Which you could have taken a lot of time to do, right? Here you could just import a CAD model, perform these mechanisms, right, and get all the relevant information that you need. Right? Next thing is, once you have done all this here, then you can, this will get integrated with MATLAB. Then you have rest of the things what we covered in MATLAB that you can also combine with it. Okay. So two things here. One is you can take this model into MATLAB to do whatever you want. Let's say like control system design or just simulation. Okay. Other thing is you can connect MATLAB to this application directly to drive it. Okay. I'll show you both the ways. Okay, let me close this. Okay. And before closing, you have to save that file as WM3. That will come here. And this is first step, first way to do. So what you have to do is you already saved that file in WM3 format. You have to take that file here. Okay. So this is that file we have already saved in WM3, and we say here open, and you say import to Simulink. Okay. Once you say import to Simulink, this get mechanics will create SimScape multibody or sim mechanics model automatically for you. So this model will be automatically created. So it has created this model. So this model all automatically created. So you can directly run it. Let's see what happens when you run it. Right. Okay. So we are able to get the same simulation inside MATLAB. So this we are able to get in that SimWise, right? So using the get mechanics, we translated a CAD to SimWise and SimWise to MATLAB, like that. Here also it is in 3 dimension, right? And you can again play back and run. So this is running under gravity. It came from there, and just plain gravity is running this. Okay. Now what all you can do here? Okay. Now around this, you can actuate this joint just the way you did it in SimWise here. You can measure some joints the way you did it here. Only thing that you cannot do here is FEA. That was happening in SimWise, right? So you cannot do FEA in MATLAB. So that is why you have to connect to SimWise, right? So once you get this imported, this is one way. You can bring it inside, right? And then how do you actuate this? It will give you this model. Okay. This is the model will be automatically created, right? Then you can select a revolute joint, and then under revolute joint you have actuation. Okay. Under a revolute joint you have actuation. So here you can actuate by torque or by motion. So you can say that move like this, it will move and calculate torque, or you give a torque and it will show you how it will move, right? Both options are there. Okay. Fine. All right. Yeah. Constraints are also important. Yeah. So this is that here. This is a revolute joint here. So revolute motor or revolute joint will come as a revolute joint here, like this, automatically. Yeah. So correct. So what happens is display is different from the other one. This is moving under gravity. Because what we have done is that we have modified it. That is a different model. So that is a different model. But you can change it. So if you have to drive this by a kind of motor, you have to just put here a sinusoidal connection to it. That's it, right? Let me see if I have that example also. Just a second. Let me see. Where is it? Yeah, here. 14B I'll close. Okay. Okay. So under this, let's say, go here. Under this, we have a couple of examples. Let let me see which example I have here. Yeah, here, so for example. Okay. So here we are actuating it using outside revolute joint. So this is a revolute joint and we are giving an external torque to it. Okay. So you can modify this once you import it, you can modify it the way you want, right? So here we are putting it as a PID control. Okay. So if I run it, okay. So you can run it as a what we are trying to do is maintain 90-degree angle for one of the joint, right? This particular joint. So it's just actuation. You can just put it here, anything. You can put motion or torque, anything. No, that will not import. That will not. Only the joint will come. Not the value. Only the joint will come. Yeah, that you have to import. That you have to put apply manually. It's an external tool. Yeah. You have to download it. Yeah. SimWise is an external tool. It's a third-party tool. It's a different tool. It is not in MATLAB. It is a partner of MATLAB. It's like both tools work together to develop this. That's what I'll show you. So this is a separate tool. This is a separate tool, but they both work together. No, it's a separate company altogether. Okay. So what happens is that some developers from SimWise, some developers from MathWorks side, they develop this technology together, right? For example, next thing what I'm going to show it to you is you will also, so one is to import. You do something in SimWise and you import it, right? That will bring everything inside Simscape, MATLAB, Simulink environment. Okay. What are the benefits of doing that is you can do controls and everything within MATLAB. If you are looking for doing FEA around, let's say, your model, then you have to go outside MATLAB and do it and come back. Okay. And how it is done is like this. Okay. So what SimWise also provides you is this block. Okay. What is this block is nothing but it's a connection. So if you see here, what it tells you is which file you are connecting to, what values will go from MATLAB to SimWise, and what values from SimWise will come to MATLAB, back into MATLAB. So here we are sending motor velocity to SimWise. SimWise is sending us FEA and position, everything. Okay. How that works? Okay. Let's put this side by side. Does it? Okay. So these are the two tools. They will open together. Okay. They will open together here. And then when I run from here, you'll see that will also start running. Okay. So MATLAB is also running here and SimWise is also running here. Both are connected through this block. Okay. And if you observe on the time, but this is the times of simulation in MATLAB, and this is the time of simulation in SimWise. Exactly same, right? The time is exactly same, and it is getting all this FEA back into MATLAB. Okay, this is very very crucial, because if you mismatch on time, it will be like a junk simulation. It does not mean anything, and it is also difficult to do, because this is running on ODE solvers. This is running on Euler solver, plus you have your master and FEA solver, right? So the time has to be matched. If that time does not match, then you'll get wrong results. Right? So this block will help you to easily connect externally to SimWise and get back results from there. So for things, let's say FEA, you cannot do it in MATLAB. So you can go here and get it done and come back like this. Okay. So not only FEA, if you see inside this scope, right? So if you see the scope, this is the position how it moves, and this is the stress values, right? So if you zoom in, you can easily see the trend. What is the trend in stress values? So it is also stress goes up, comes down, goes up, comes down, goes up, comes down. Right? That's because it's a sinusoidal motion. So stress forces generated are also sinusoidal. So you get this kind of motion. So you could do this complete end-to-end thing with SimWise and MATLAB together. Right? So for mechanical guys, it is at times easy because they can have this complete system ready and press one button and everything will get solved together. Motion, FEA, controls, whatever you want to do. Right? So this is very useful for today's complex type of problems that we work on sometimes. Okay. Then this is one. Okay. Any questions on this? So here there are some. That's what wanted to show you. Let me close this example. So it's not only FEA. What will happen is when you open this, okay, and select this body, okay, there are a couple of things it can do here. Okay. So, for example, you could do FEA, you could do heat transfer, sound, then you could do, there is one more here, sound, surface, texture, user loads, this one. Yeah, mainly heat and sound. Right? Material I have already showed you. So what you do is, when you want to enable heat, right? So now you don't see heat option. So when you enable heat, then it will come. Okay. So what you do is, then you have to what you want to do with heat. So you can say temperature induced stress you want to do, or you want to do heat generation or dissipation, like that. So you can also include that. You could also do something like sound. So sound will do is what will happen when it collides with something, what kind of sound it creates, or when in motion, what kind of sound it will create, like a fan or something like that. So those kind of things also you could simulate. So these things are not there in MATLAB. So when you use that connection block, you can do everything here and transfer it back to MATLAB. Okay. That is the whole idea. Okay. Then this is fine. Okay. Next thing is, once you go here, I can show you one more example. One more very important and very powerful technique here is contact modeling. Okay. So under contact modeling, let me show you one example on that. The wrong file. Okay, here what we are trying to do is, so this is a real problem. Where do you apply all this? So here we would like to design, let's say, a truck. Okay, we want to design a truck, and we want to calculate how much engine power is required for a truck to climb and what are the designs it needs. So what we have done is, if you see here, okay, so we have created a complete like a road profile here. So there is a road, there is a ramp. Okay, you can see it from this condition. So this is a ramp, okay, where we want to calculate that minimum it should be able to climb up this kind of a ramp. Okay, this is a detailed model of initial level like prototype, right, multi-axle truck. Okay, and what happened? Oops, disconnection. It'll come back. Yeah. Okay, so it is also, if I hide this road and if you go into its detail, it's got suspension model, tire models, right, joints and everything. Okay. Okay. Now, what we want to do here. So let's zoom in at this size. Let's not save it, open it again, so that I have some data already stored. So what I want to do is, from MATLAB, I will actuate this model and understand how the vehicle is driving. Based on that, I will supply more engine torque, and then I will be able to exactly get how much torque is needed for the vehicle to climb. Okay. Let me open it again. And here I'm just logging the velocity and the position of the vehicle. Okay. You see here? Just zoom in here. So interesting thing to see is that this vehicle is in the air when it starts. The tires and road, they don't have any contact or joint definition. It's just contact, and the torque is being applied on these wheels. So every time we are trying to understand what will happen to this suspension and how it will behave, right, when it is on the climb. Okay. And here you can see you are able to get what is the x position of the vehicle, right? What is the x position, x velocity, z position, z velocity, right? So you are getting it back from the SimWise model, right? If you had to do this in MATLAB only or in with your equations, it will take a lot of time. Just to take data from here and there, solve something in this tool, take it to the other tool, do it there and come back to one tool, right? So you can keep doing that back and forth, or you can use something like this, which allows you to do, everything in one go. Okay. So this takes a lot of time, contact modeling, but I'll show you one video on this. Yeah. SimWise. SimWise is running separately. Right. You have to install SimWise and also MATLAB together on the same PC. You can get it from the website actually directly. their website is, if you see here, no, you have to pay. It's for education. You might also get a trial also for this. Optimize, yes. Yeah. Actually, the idea is, so let's say for FEA, the PD toolbox, or FEA, there is no toolbox. You might have some downloaded someone else toolbox. You could do FEA. Also, many people have done it. I have some examples, but FEA is not suited for MATLAB. Right? If you want to do FEA in MATLAB, MATLAB is not the right application. There are better applications other than MATLAB, which are better for FEA. That is why we don't build anything inside MATLAB for FEA. We plan to do something like maybe have a simple FEA inside, but like a flexible body, but not a full-fledged FEA. Full-fledged FEA only other tools can do better, right? Yeah. So like here, so this is a completed model where you can see the vehicle moving on the ramp, and you can see how it works, whether it will work or not, right? So you see when it goes on the edge, you will be able to see the vehicle dynamics. It takes a lot of time to simulate something like this, right? This is one, and suspension also you can actually view like this here. You are getting all these forces and everything. Okay. Like this here. So when I'm on the bump. So this is all contacts modeling. Okay. What happens is here, there is no joints. It is just when it comes in contact with the body, it will just behave like a natural physics phenomena. That's why you can solve it, because you cannot have any kind of joint like this. Okay. So that is one. Okay. Now once you have understood how you bring something from CAD to SimWise to MATLAB, or do a co-simulation, you can then integrate everything into one. What I talked about when I showed you the video from Terry Denry. Okay, so let me show you one example there. So let me open this file. So this file is also what you saw in that video. Okay. So if you see, it is a highest level view of the model. If you go inside these subsystem blocks, you will go into depths. Okay. So this contains all the mechanics, electronics. This contains your controller, and this contains your command. What do you want, right? And how it solves is like this. Let it start. Anyways, okay. So this is that plate that is moving. Okay. So these positions are automatically calculated by inverse kinematics, and these motors are actually modeled there. So these are not depictions. I'll show you how they are modeled. So it's a big, complete multi-domain model which has mechanical, electrical, controls, inverse kinematic, all those things embedded into. Next step is you can attach a camera to this joint and do image processing and pick and place. You know, like I showed you one of the example videos. So it can continue. I'll just stop it. Now, if you look at the mechanics and electrical part here, so this is your mechanical part, which is automatically imported. Okay, so this is what he was showing. Okay, so this is automatically imported from that CAD model. So if you go inside, you'll get this solid body, and all the parts will be there. Okay, right. And all the parts are there, and then this is your electronics part, which is your motors part. Okay, so this is your motor. Okay, so how many motors we have here? Around 1, 2, 3, 4, 5 motors here, if you see. Okay, 5 motors for turntable, bicep, forearm, wrist, and hand. Okay, if you go inside this, okay, so you have this DC motors, right? Turntable servo motors, right? So for each motor there is a PID control, okay, and there is a DC motor. Right. So I am using a sim electronics DC motor. Okay. So you can just define all the parameters here. Okay. The configuration, the parameters, right, and just say OK. Right. So basically, this is what we are trying to do. So you see, you have an electrical model, you have a mechanical model. When it moves, you can understand what is the load on the mechanical system, what is the current that is being consumed, what is the power consumed by the system, everything in one model. Okay. Now there is also one more task here. If you see, every motor has a PID controller. This motor also has a PID controller, this motor also has, and similarly others. Right. So I might have shown yesterday how to tune one PID. Okay. How do you tune one PID? Now tuning 6 is a different way. Right? How do you tune a 6 one? Is you have to go from here. Okay. So you have to go from analysis, control design, and control system tuner. Okay. So when you want, you can still hit that button, but it will not tune for the complete system level objective. Okay. So one PID, one motor, it's fine, you know, because it's only one PID. But when you have 2 or more, they interact with each other. Okay. So it is kind of a linked problem. Okay. So how this is done is, yeah. So you can go to control system tuner, you can select the blocks. Maybe I'll just guide you through this. Control system design, control system tuner. Okay. What it will do is, once you get this here, so you have to select the tuned blocks. Okay. So what you do is, go to tuning, select blocks. Okay. And you say add blocks. Okay. It will look at all the blocks in the model and then show you options. So we have blocks in controller. Okay, let's go inside controller. So you see here, we start getting PID. So you can select all these PIDs inside. Select all them, and then say OK. Okay. So it is going to select all the PIDs that you want to tune at one go. So it's added. Okay. So you have 5 controllers. Now the tuning goals. Okay. So you can select a tuning goal. What kind of tuning goal you want? If you want a normal PID tuning, you will go for tracking step commands. Okay. You have to add a reference signal, response, and output. So you select signal from model. So basically it's nothing but you can go back to a model and you can say in controller, go inside controller and you say these are your inputs. Okay. Oh, sorry. Okay. Inside that, add a signal. Sorry, select a signal. And then you come here and then you say, what is it? Select signal from model. Oh, maybe inside this I have to go. And yeah, only this. Yeah, so you see here, it will select that signal and you say add. Right? And then you will have to select the output. This has been added. Okay. Then you select the output. Similarly, suddenly it has become very slow. So output also you can see directly you can select from signal. So this is your output. And you say OK. Okay. And then so you have selected the input signal, output signal. You can select the time constant if you want to some desired, how much you want to match, and say apply and OK. Okay. Once you do all this, basically it will give you, you are ready for start tuning all those 6 PIDs. Okay. What is it? Oh, 1536. Did I select something wrong? Maybe this one here. Combined signal. Oh, there is something wrong in this. No problem. I'm selecting the wrong signal here. I think this is the command. This signal has to be selected actually inside. Suddenly it started becoming really slow. Alright, no problem. Let me show it to you. For this moment I have one recording for this also. Just a second. So just a second where that I've kept the video. I think it's this one. Okay. Basically, let me come here. So this is the one big video which takes every step into account and how it is done. Already covered all the thing. Main part is the controller part. Okay. Here. Okay. So here also we are using the same model, right? So we go to analysis and control system tuner. This one. Okay. Snapshot you can also take if you want to have some starting point. Okay. Then you select all these PID. Okay. Then you can choose whichever you want. Most of the time it is tracking a step command if you have a command to follow. Then you can add a signal. So you can add one reference and the other one is this here. Okay. Similarly for output, you can select this signal here. Okay, all signals, and then you say OK. So basically you'll get this kind of a matrix, 6 by 6 matrix, and this you have to tune. So this is the effect of one PID on all others, this PID on all others, and this PID on all others PID, like that. So basically when you tune it, this will be tuned under this 1, 1, 2, 2, this line. Okay. So this can be used in any areas. Whenever you have multiple PIDs, this is how you tune. Right? You don't tune it using a PID tune button. Right? That is only for one single PID. Okay? This is also known as multi-loop PID tuning, multi-loop controller design. Right? Many applications are there. When you have a complex system where it has multiple control peripherals, then you use this kind of technology. Control system tuner. Yeah. Right. Okay. Then yes, most of the things we have covered. So from here we have covered almost all the things that we wanted to cover. So these slides will be there. I will also give you all these videos separately. Right? So these videos I will give you separately. For example, you can have stress, buckling, thermal, how you can do co-simulation. There is one more video which I have made from Lego, and how it compares with simulation. Right? So this is a robo arm from Lego, and this is the model of simulation. Right? So same code is running on this controller code, on this Lego robot arm, and you can see how it will compare with the simulation and the actual robot. Right? This is how it moves in the simulation and actual. And you can see here what are the this is the position, right? Desired and what the motor follows. So there is some error in that. So you can actually compare your simulation work with your actual prototype. So Lego, Raspberry Pi, Arduino are really good for performing these kind of comparisons. Okay. And the one that we saw yesterday as an example is here. So this is the whole idea. This is the workflow going from a CAD file to a prototype. Right? What are the different stages? Is basically nothing but you have a CAD model, you import it, you bring it inside Simulink, simulate it, create all the controller design and everything, generate C code, code generation part, deploy it onto a controller, and you can see this actually working. Right? So that is the whole idea. This is already there. Example on the MATLAB Central. I'll give you all the links there. Right? So this is, you can apply this same principle to any of your projects. Right? This is actually called model-based design. So you start with some model and actually end up with a prototype. Right? Everything in one go. Model, test, design, verify, code generate, create a prototype. Like that. Okay? So this is what I had. You have my contacts also here. You can reach out to me on my email. Sometimes I may not pick up phone because I may be presenting somewhere. So bear with me, right? So best way to reach is by email, basically. Because email, if I go back, I basically take a moment and reply to those emails. Right? And I can send you information also on that. Okay? So any questions or queries you have, I can take a few moments and answer something from here that you guys have. Could be anything, not necessarily on things I talked about. It could be your own problem statements or something. So that I believe it's not there, where you can import ANSYS CFD model into MATLAB and generate a C code. Yeah. QuickSim. No, that is not of MATLAB. So there are a lot of toolboxes, as you rightly said. You can actually go to your MATLAB Central. Okay. So when you go to MATLAB Central, you will get a lot of files there, and even apps. So if you see here in the new MATLAB that what I'm using, apps, so you have an option to get more apps here, right? So get more apps. So you can get more apps from MathWorks, from other people. You can create your own app also, package app. Whatever you make, you can actually make an app. So a lot of apps are there which are made by general public, and which are made by MathWorks are all here. Some are there on the MATLAB Central also, created by people from MathWorks. That is also there. Yeah. For fault analysis. Right. Fault analysis is very much in demand. Actually, a lot of people want to simulate a fault. As of now, we don't have direct way to simulate a fault, but you can make your own system to detect a fault and take some action based on that. Right now, there is not there, but you can, using the basic blocks, what you see here in Simulink, you can make a fault detection system. So if you see here, probably in examples, if you go, you can get some examples also here. Like for example, if you see here, lithium ion battery pack with fault management, fault detection using data-based models, right? So there are some, but as a toolbox we don't have, but there are some examples how to model it, right? So you just look at that. Yeah. Yeah, only for electrical system. Electrical, okay. In electrical it is there, yes. If you have a general purpose fault, then that is different. If you're asking for electrical fault, then you have in electric power system, where you can simulate a fault, like 3-phase fault, 2-phase fault, it's already there. All three, using that fault simulation. You can actually see some examples also here. From Sim Power Systems, Simscape, here. If you see here, so you will see there will be a lot of examples around this. Simple circuit, 3-phase model. So under 3-phase model, at times you can put a fault. In some example, you will see it. Mostly it is in let's say transmission. So for example, here only you can put a fault, and one example is when you do this is reactive power management. Okay. Power window, here. So is there a fault here somewhere? Just I'm checking. Like this here, but this is a 3-phase fault, right? So you can simulate all the transient steady case also, both. So you have to select this power GUI, double click it and change it. You can simulate it. Best way to start is with the examples basically. So this is of HVDC transmission. Faults are typically modeled by them to understand whether their controller will be able to manage the reactive power or not, like that. So it is important there. So you can use it. general purpose fault, what I understood is not there, but it is very much in need by general science community. Many people would like to simulate faults, blocks that can be simulated as a fault, like failure in joints, failure in springs, failure is in various things around. Okay, so those faults we are working on that. Maybe that will also be added soon. 3D? 3D plots. 3D plots is there. Just explore this option here. So you have a lot of options here. Plot 3D is there. Plot 3 is there. So when you just hold on for some time, it will show you how to use it. It will just need 3 data points, right? So you say plot X, Y, Z. Okay, very easily you can do it. Sorry? Animation, not in the plot. You have to hold it. You have to hold and plot like that. So you have to do. Actually, yeah. Okay. Original. Okay. Maybe. So what I'll do is maybe you store some values here like this. All right. 1 to 10. Okay. And y is sign of, let's say, x. Okay. Then you plot it, x comma y. Okay. So best way you can use it as a save as here. I think they have given option. Earlier you can't save this as a picture, right? So you see here a lot of options are there. If you use this, better is to use a let's say TIFF file, right? If you see TIFF, no compression. Okay. So TIFF is very good for having general purpose image. 50? Okay. 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 So for example here, let's see untitled.tiff. So if I open this TIFF file, right? So this, you might be talking about this. Is it? Blurry, yeah. Yeah. So what you have to do is, you have to try to save it with different options here. For it. It is not. Okay, it's not too early. Sure. Okay. Okay, maybe, yeah. I've also seen that. Yeah, because I have seen meta file as an option, but I have not tried it. It's been while I have written a report. Yeah. Word. Right. Any other thing? Otherwise, then I'll be here for some time. Anything you want to know? Sure. Study material, I'm already preparing some more information from today. So basically what I will be sharing is some videos that I showed, this presentation material as well as demos. So demos, I'm also including some more from day 2 also here. Yeah. This, absolutely. This you will get. This I'll also, if this you want straight away, that I can also mail through her, and everybody will get an email directly. right? Or I can do it as a upload to Google Drive and share it with you all, where you can download it, right? Only problem is, I mean, Shirali coordinator has all the details, so I can directly give her the link and she will share everything to you that way. But today only I will give the upload all this and send the link. So maybe today or tomorrow you should expect that you will get this. PPT I will also give her separately, so that demos might take time if she wants to upload. But PPT she should be able to email everything to you, right? So this is big. It will not come by email, so I'll zip it, make it smaller, and then so that PPT at least you can get, right? Sure. So I'll be here. Thank you. All right.